just like I did for the last exam, I'm going to make a video that's solutions to the problems. So you can check it out, see the problems you struggled with, how to do them. So, number one, 4 antiderivatives. They all are pretty basic, like homework. So on the first one here, recognize those radicals can be written as powers. X to the 1/2 is the square root, x to the 1/3, so we're just going to raise the power from 1/2 to 3/2. Divide by that, or since it's a fraction, we'll multiply by 2/3. Same thing over here, the cube root is x to the 1/3, add 1, you get x to the 4/3. And again, dividing by that or multiplying by its reciprocal, you get 3/4. I'm not going to add plus c here, but of course we would want to add it to all of these problems. Second one's a polynomial. I'm not going to say anything about it. I think everybody got it right. The third one here, we saw this on the homework, so the way it's written, we don't really have any idea what the antiderivative is, but we can simplify it. And if you just divide that x across all the terms, the x that's in the denominator, then we get 4x plus 2 minus 1 over x. And so we get a pretty simple antiderivative, 2x squared plus 2x. And then the minus 1 over x, of course, is minus the log of the absolute value of x, again, plus c. On part D, we have, 4 functions added together, but all 4 of them, we should be able to recognize the antiderivative. Antiderivative of secant squared is tangent. 3e to the x is 3e to the x. Minus 5 over x is minus 5, natural log of the absolute value of x. And the antiderivative of sine is negative cosine. The 3 comes along for the ride. So there we go. 4 antiderivatives, hopefully 20 points in the books. On number 2 here, another 20 points. It's just, I give you the derivatives. I don't tell you the function. I want you to use information from derivatives to answer these questions. We had a few problems on the review, problems I posted where you were not given the function, but given the first or second derivatives. So the first one, part A, determine the critical points. Well, this one is pretty simple. So simple that maybe you didn't trust it and you tried to make it complicated. I'm going to set that equal to 0. There's only one number that makes it 0. A lot of the common mistake was to somehow deal with that denominator and think that plus or minus 2 were important points, but they're not. That denominator is never, ever negative. In fact, it's always bigger than or equal to 4. So it doesn't contribute any critical points. You just take the derivative, set it equal to 0, and I believe that a lot of you can just look at that and say x equals 0. So I didn't require you to show your work or any such thing. There's one critical point, it's at 0. Part B, where is it increasing? Well, if I draw a sine graph, we need to label it. A lot of you didn't do that. And this is a sine graph for the derivative. As we mentioned in A, it's equal to 0 at 0, and it's clear it changes sign. If x is positive, the derivative is positive. And if x is negative, the derivative is negative. For an increasing function, we need a positive derivative. So 0 to infinity. And again, I think a lot of you could just look at this derivative and just say it's going to be positive if x is positive and come up with this answer. On part C, does f have any local extreme values? If so, identify them. So every local extreme value occurs at a critical point. So we have the potential for one. And how do we decide? We use the first derivative test or the second. I'm going to do both just so you can see them side by side. The first derivative test, all the information is in this sine graph right here. The derivative changes sign from negative to positive. Minus means decreasing. Positive means increasing, and so therefore we have a local min by the first derivative test. And we could say just what I said, that is we want to justify our answer. F prime changes from negative to positive. Or you could just refer to the sign graphs if it's properly labeled from negative to positive. All right, second derivative test may be even easier because the second derivative is sitting right here. If it were not sitting here, then we would use the first derivative test and be done with it. So what I'm going to do is plug my critical point in, and it should be clear it's positive. I'll write what we get, although I would let you just say it's positive because it's pretty obvious. So 0 plus 4 squared. Again, we don't care about the number is. All we care is it positive or negative? So positive second derivative means concave up, and therefore by the second derivative test, we have a local min. So either one, not both. One of them does the job. A lot of people did part C and didn't ever reference the test, and that's how we decide. So if I can work it out, you'll see a problem like this again. You know, maybe I won't calculate the derivatives, but I'll give you a chance to show me you can use these tests appropriately. Finally, the one that actually takes a little bit of work, on what intervals is the graph concave up? I should have said at the beginning that there are actually two versions of this test. This one I'm working on is the one the students at 8 o'clock took. There was another one where mostly, just constants were changed, so the answers were different, that the students in the 12 o'clock and 1 o'clock sections took. There actually was a third version for people who had to take it from quarantine. And for technical reasons, excuse me, I did have to change one problem. We'll talk about it shortly. It's problem number 3. So somebody pointed out actually my derivative is wrong, my second derivative. But you can work with it. It actually should be 8 minus 2x squared. Somebody sent me an email. Thank you very much. So I get a 98 on this test. I lose a couple points. And maybe you would say, well, if I'd had the right derivative, it would be easier. But, not really. So we determine concavity by the sign of the second derivative, just like we talked about up here when we were using the second derivative test. So I need to know, where is it positive and where is it negative? Positive means concave up, negative means concave down. And again, the denominator is never, ever negative. In fact, it's always bigger than 16. So the sign is totally determined by the numerator, and that can be negative. In fact, we recognize a quadratic function, factor the 4 out, and we get 2 minus x squared. And we recognize that, you can factor it further, or you could just analyze it. I think either one does the job. Square root 2 plus x, square root 2 minus x. So we have a sign change at plus and minus square root 2. I think it's clear because of this minus sign right there that eventually it's going to turn negative. So the region far to the right is negative. Let's label this. This is f double prime. Plus minus. So it's positive between the negative square root 2 and the positive square root 2. And for my bad derivative, this is the answer. During the exam, no one mentioned to me that this derivative was wrong. I tried to grade it. If I saw evidence that you were worried about that, I gave you the benefit of the doubt. That was my plan. I never did see evidence of it. And so I'm looking for a negative square root 2, square root 2. So if you couldn't quite see how to factor this, just think about the 2 minus x squared as a function. It's, excuse me, it's a parabola. It opens down, and the 2 lifts it up 2 units. So you could look at that, and then you could just find where does it cross the axis. And if we recognize it's a parabola, we know there are 2 values. A common mistake here was to miss this guy, and then people would say negative infinity to the square root 2, but there's a sign change back here. So we need to be careful. We know what quadratics look like, so you could factor it, you could think of it as a quadratic, whichever. If you think of it as a quadratic, then you just set it equal to 0 and solve and get our 2 sign change points. All right, that's page 1. I'll post it, and the next video will be on page 2.